Okay, welcome all of you. I thank you all to be in the classroom. And we have been talking about postulates of quantum mechanics, right? And I gave you the introduction of the postulates. We talked about the 5 fundamental postulates of quantum mechanics. And today's target is again to move on in the same framework to get a deeper understanding of these postulates, because foundation is always it's always important to build anything on it. Now, I think to bring you close to the quantum laws, to bring you close to the weirdness that we find mathematically in quantum mechanics, I will take you to a journey. I'll take you to a journey in which I will try to describe the meaning of observables and the measurements that we take in quantum mechanics. If you imagine that you have a temple, and in this temple there is an oracle. Now, oracle is basically a metaphor that was used in ancient Greeks. Oracle, you should sense this word, because I am giving a name oracle to a person who is inside the temple. But finally, you should treat this oracle as nature itself. So what happens is, you have a village, and in this village you have a temple, and in the temple there is an oracle, and villagers have they usually have problems. Okay, so you want to have a person. If you have a problem, you will go to someone you believe in. Okay, it can be the president of that village, it can be somebody else, but I am taking an oracle inside that temple. Okay, and this oracle is a silent person, he's not talking. But when somebody goes there, he goes with a problem. Okay, now there can be a range of problems. Somebody wants rain to fall. Somebody wants that their kids should flourish. Somebody wants the marriage of his or her daughter or son. Right? So there are a range of questions that the villagers can ask to this oracle. But oracle has a set of answers. It has a set of answers already in him. But he is not talking, he's silent. So what happens if any villager has a problem? What he'll do, he will go to the temple, he will enter, there is an oracle, and he will tell him the problem. And oracle will choose one of the many solutions that he has for the problems. But the problem should be well defined. Okay? So what is happening? Villager 1 is coming with the problem of rains. The oracle responds, and he gives the answer that this villager needs. Villager B goes, villager C goes, and the oracle gives answer in accordance with the question. Getting my point? So there are well-defined things. My daughter getting married, the rainfall, the crops, the flood. There are a range of defined problems. and the villagers go with a particular problem, the oracle responds and answers and gives an answer to that particular question. But if there is a question which is not a right question, now a villager goes with a question which is not a defined question. It is not a Hermitian operator. He goes with that question and asks the question to the oracle. The oracle answers, but the answer is not clear. He is giving a weird answer. The answer does not satisfy the villager. Are you getting my point? What am I trying to tell you? So, this story in which you have an oracle, which I previously told you, you should finally compare it with the nature itself. And the villagers having different set of problems. The villagers act as operators. And the oracle, when the villager goes to the oracle, it operates on oracle, and oracle responds to the right question. If the villager asks a question about the agriculture, now I can compare this agriculture with, say for example, momentum operator. So when the villager enters the temple using a state vector, the oracle responds, and responds discreetly, responds with the particular answers to the problem, gives you the eigenvalues of the momentum. So the situation between the villagers and the oracle sitting in a temple is same as that of an operator and the outcome of a measurement. Getting my point? This is how nature responds. So it doesn't mean that you can have all types of operators. You cannot have an operator of emotions right now as long as we understand quantum mechanics. When you will ask a question based on the emotions to the oracle, maybe the oracle will confuse. He will give you a weird answer. So you have a particular set of operators. They act on the oracle, and oracle responds. He has many answers available to him. He has a sea of answers available to him. But he knows what answer he has to give to the question that's asked to him. Are you getting my point? I can turn back the same story to the same oracle and the same villagers. Now there is a villager, he holds a dice in his hand. We understand a dice, 1, 2, 3, 4, 5, 6. He goes with the dice to the oracle. But he already knows that if I know the initial conditions with which I will throw this dice, I will exactly predict what will be the outcome of that experiment. Getting my point? He knows classical physics. And classical physics purely allows us. It tells us that if you know the right conditions, if you know the right forces acting on the dice, you will exactly predict the outcome. Getting my point? And he goes with the dice to the oracle. When he goes with the dice to the oracle, the answer from the oracle comes. It tells there is 1, there is 2, there is 3, there is 4, there is 5, there is 6. there are all of these possibilities. These are the possible outcomes. This is the knowledge of the oracle. Oracle knows everything about it. But when you ask the particular question, it responds to that and tells you this dice is in all the states. Are you getting my point? So this is how we can imagine the physicality of this quantum mechanics. And what we have been talking about? We have been talking about the postulate of observables. We have been talking about the operators. In classical mechanics, we have observables. Corresponding to these observables, we have corresponding operators. So what observables we have in classical physics? Say for example, we have a classical kind of thing, and we have quantum. So in classical we have position. In quantum we have position operator. In classical you have momentum P. In quantum, corresponding to P, what you have? You have an operator that is minus IH cross if you take only one dimension, or you can put a del here. If you have energy as an observable in the classical physics, corresponding to this you have an operator in quantum mechanics that is IH cross dou by dou T. Are you getting my point? Similarly, we can talk about the Hamiltonian in the classical domain. And corresponding to the Hamiltonian, we have a Hamiltonian operator. So Hamiltonian can be treated as sum of kinetic energy plus potential energy. This is the observable in the classical physics. Now corresponding to this observable, we have an operator, kinetic energy operator plus potential energy operator. And for kinetic energy, you have P squared by 2m. For potential energy, if I assume along x, V of x. In quantum mechanics, you have an operator. So that will be minus h cross squared by 2m del squared. Plus operator of potential V of x. So this is how the story goes. So what you have? You have operators. Okay? You have operators and you have measurements. You measure your things using operators. Right? Clear?
Yes, sir.
Okay. Now let's talk about, suppose I take a state, I choose a state psi, and I define this state as, say for example, a e to the power of iota p r. I take the magnitude. Okay? Otherwise it has to be p dot r. Now, what I do with this is a state, right? It's a state vector, right? Defining in terms of a function, an exponential function that depends on the momentum and the position, right? So, if I operate on this state, now suppose I choose momentum operator. Momentum operator. What is that? That is P. I act this P on psi. Right? What I'll get? I will get P and psi. Now let us evaluate this. Why should I write P here? Let me write anything like A, which is a number. Now whatever it is, we will see that. Now what am I doing? I am operating on this state by a momentum operator. And the state is already defined. So I can calculate it. Okay? So I can calculate it. So P of A e to the power of iota P r. Okay? Clear? This is it. But what is P? P is minus IH cross dou by dou x. Let me choose R here. Exclusively dependent on R. A of e to the power of iota P dot R. Am I right?
Yes, sir.
So minus IH cross is like this. And then A is a constant, it will come out. Then the differential of an exponential is an exponential. But you have to take the internal derivative of the exponent. So for the exponent, what you have? You have iota P. Now this P is not an operator, it's a number. Okay? E to the power of I P dot R. So this will give us iota square. Iota square is minus 1. Minus will multiply with minus, will get plus. So it is H cross P. So it is H cross P A e to the power of I P dot R. Clear? So what I did, I used an operator. I acted this operator on the state psi. Psi was defined. I obtained the eigenvalue H cross P and I got back my state. This is how operators work in quantum mechanics. So when you operate on the state that's defined, then you obtain the eigenvalues. You get the real numbers. And the operator that you have used here is a Hermitian operator. Hermitian operator I have already talked about. Okay? So, acting upon the momentum operator on the state psi leads to H cross P and your psi is back. Is this clear? Okay. Now let's move a little bit further. Let's try to understand this measurement problem in quantum mechanics. And the measurement problem, as I said before in my previous lectures, once you look at the system behaves in a different way. It gives you one particular answer. But that answer, the system gives you out of many answers that are available to him. You remember the oracle. Oracle has many answers. And what he's doing, when he gets the right question, he chooses the right answer out of all the answers the oracle knows. Getting my point? So this is what is happening here. That means in quantum mechanics, you have a measurement problem. And measurement is something that when you measure something, the oracle responds in accordance with your measurement. Let us understand it a little bit numerically. What am I trying to say? Now think of an electron, assuming that you have an electron in an orbit. Okay? Assuming that you have an electron. Okay? Take the simplest of atoms, hydrogen atom. And how much energy you want to get this electron out of this hydrogen atom? 13.6 electron volts. You want 13.6 electron volts to knock this electron out of its shell. right? Now imagine a photon, okay? I imagine a photon. What is the size of an atom nearly on an average? On an average, the size of an atom is nearly 10 to the power of minus 10 meters. What you also call as 1 angstrom, right? Now, if you want to make a collision with the electron, you must have a wavelength of the order of the size of an atom. In fact, it should be less than that of this wavelength. Are we getting my point? So, I want to calculate the energy now. E. I have to use a photon to interact with this electron. And this electron is bound to the nucleus of a hydrogen atom. Because I cannot see without using a photon. Can I see without using a photon? I cannot see. My instrument will not see. My instrument has to have the detectors which respond to particular frequencies of the photons. Even those photons may not be visible to us. You have an electromagnetic spectrum. Is everything visible to us? No. You have only the visible portion. But there are other photons of other wavelengths. Getting my point? So, what is the famous energy for energy? E is equal to h nu. Right? I want to see the position of my electron. This is my target. I want to see the position of my electron. Right? And to see, I will use a photon, and that photon has an energy equal to h nu. And since the electron is roaming around the nucleus of whose size is of the order of 1 angstrom, I will use a photon whose wavelength is 1 angstrom. Right? So, h is what? Planck's constant. What is that? 6.6. 6.626. Let me take 6.6 times 10 to the power of minus 34 joules second. Then multiply it with the velocity of light, that is 3 times 10 to the power of 8 meter per second, divide by lambda. So lambda is how much? 10 to the power of minus 10 meters. Because nu is c by lambda, so this is hc by lambda. Now when you will calculate this, you will get your answer in terms of joules. You will divide it by 1.6 times 10 to the power of minus 19, and you will get your answer in terms of electron volts. And you know how much energy you will get? Yes? How much energy you will get? You will get the energy that's very, very greater than that of 13.6 electron volts. That means the moment photon will interact, you will lose the position of the electron. Are you getting my point? So this is how the act of measurement disturbs the system. So that's why everything in the quantum domain is not completely predictable. You can predict here only what? You can only predict here probabilities. You can only predict here probabilities. You cannot predict the classical way of throwing a dice or classical way of throwing a coin. If you know the right conditions for a coin, you can exactly predict the outcome of a toss, which we numerically calculate as 1 by 2. But the laws of physics allow us, they tell us that you can exactly predict what will be the outcome of that coin. But that's not the case in the framework of quantum mechanics. Because in the framework of quantum mechanics, what do you have? You can have head and tail as a result at the same point of time. Are you getting my point? An electron can have spin up and spin down at the same point of time. And from spin up to spin down, there are infinite possibilities. So your electron can have it can be in infinite number of states. It can be infinite number of states before your measurements. But the moment you will make a measurement, it will give you an answer. It will respond to your question. The question that the villager was asking to the oracle inside the temple. Are you getting my point? It will give you answer to your question. And if your question is weird, it will give you a weird answer. Now there is another thing like angular momentum. Let's write down angular momentum in terms of operators. We can do that, okay? So what is angular momentum? Okay, angular momentum is R cross P, am I right? Okay, so L, okay, R is your, if I write it in Cartesian coordinates, it will be X, I cap plus Y, J cap plus Z, K cap. And then you will have momentum, that is Px, I cap plus Py, J cap plus Pz, K cap. So this is my observable in classical mechanics. I want to write its corresponding operator in quantum mechanics. That's my target. Now you have R, okay, and you have P, and you have to take the cross product between the two. So you can write down this in the form of a determinant, okay? So I can say my vector L is a determinant of I, J, and K. Then I can write X, Y, and Z. Then I can write Px, Py, and Pz. But you have to keep one thing in your mind. For Px, what you have? For Px, you have an operator. Px cap. What is that? That's minus IH cross dou by dou x. And same story will go with X, Y, and Z. Are you getting it? Okay, so I can open this. Yeah, it will be I times. Yeah, you will have Y P Z minus Z P Y. Okay, then you will have minus J times J, this and this will go. So X P Z minus Z P X. And then you will have plus K. So K X P Y Y P X plus K X P Y minus Y P X. Right? And in the left hand side, what you have? You have the angular momentum vector in 3 dimensions. And you can write this L as Lx I cap plus Ly j cap plus Lz k cap. So this equation can be correct only if the coefficients of i's, j's, and k are equal. So I can write down Lx. What is Lx then?
Y P Z minus.
Yeah, tell me that. Lx is?
Y P Z.
Lx is y p z minus z p y. This is Lx. Come on, tell me what will be Ly?
X P Z.
X p z minus
Z P X.
z p x. Okay. Then you have Lz is what?
X P Y.
X p y minus
Y P X.
y p x. Now replace these observables by their corresponding operators. What will come? In the first case, what you will get? Come on, so I can replace this Lx by operator, operator, and operator. So for PZ, what I will write? I will write dou by dou Z. Okay? So here I will write dou by dou Z minus dou by dou Y. Are you getting?
Yes, sir.
Dou by dou Y. But what will be outside? Minus IH cross. Right?
Yes, sir.
So I think we can do the next. So PZ is again here. So I'm going to write here dou by dou Z. So Px is here. I'm going to write for this as dou by dou x. And here again you will have for Py, I'll be using dou by dou y. For Px, I'll be using dou by dou x. So this will also be multiplied by minus IH cross. This will also be multiplied by minus IH cross. So these are your angular momentum operators in quantum mechanics in the framework of Cartesian coordinates. Right? You got the idea?
Yes, sir.
Is this clear to you?
Yes, sir.
Yeah? If you have any questions, you can ask me. Yeah? You want to ask me anything?
Yes, sir.
Okay, bye. See you.